So quantum computing, very generally, is the idea of using the rules of quantum mechanics to do meaningful tasks like computation. It actually started from classical computing because, well, if you think about your phone or your computer you have today, you may have noticed that they've stopped getting much better. Maybe the iPhone gets a slightly better camera every year, but it's stopped being revolutionary. There's a reason for this. The transistors that make up your classical computer have been shrinking and shrinking to the point where they are today, but now the ability to shrink them further is getting limited by the rules of quantum mechanics. It's getting limited by the fact that we're just a few atoms, not millions or billions of atoms in these transistors. And at that point, it becomes very difficult to continue going. Some of us who study quantum computing take this as an advantage rather than a challenge, and we say, okay, well then the rules of the universe are quantum mechanics. What can we do with that? And the answer is we can actually do a lot. So one of the big breakthroughs in the field of quantum computing came with what's known as Shor's algorithm, which is an algorithm for using a quantum computer to factor very large numbers. It may sound abstract and mathematical, but the truth is, factoring large numbers is exactly what your email encryptions assumes is hard. And as soon as we know how to do it, I can access your emails, I can access your credit cards. The ability to do this would have real meaningful impact on society. And beyond that, simply being able to do certain computational tasks using the rule of quantum mechanics would allow for a very important future. So that's where we're going as a field. We're trying to understand and improve quantum computers in order to eventually get to that goal. Today, there's been a massive amount of development where people can control quantum mechanical degrees of freedoms in atoms, in pieces of superconductor, in defect centers in diamond, and so on, to control and manipulate them one by one. Unfortunately, once you go from 1 to 2 to 10 to 100, the problem becomes very challenging. And at the level of 100 quantum pieces of information, you don't have perfect control. You have the environment surrounding us affecting your ability to manipulate this quantum system. You have what's called a noisy quantum device. So today, groups such as mine are investigating what you can actually do with these noisy quantum devices. And one of the big things that we're working on is trying to use these controllable noisy quantum devices, a noisy computer, to solve other noisy quantum mechanical problems, of which there are a huge number that people care about. Photosynthesis is widely believed to be a noisy quantum process. Drug binding, many problems in quantum chemistry and driven materials, they all share this idea that you have a lot of important quantum mechanics happening in the presence of an environment that changes just a little bit their quantum coherence. And we're trying to study this using tools from what's called many-body physics, the study of how many different particles interact with each other. That's the field that I traditionally came out of, and there we have a massive amount of understanding of what you can do by studying emergent properties like magnetism or conductivity in metals, things that we know how to describe even if the microscopic elements aren't perfect. Taking these ideas, applying them in the context of quantum computing, we're hoping to uncover some real meaningful impacts of quantum computers in the next couple of years. Now, one of the things that UTD is very focused on is not just what we can do today, but what we can do in the future. So in the future, people will continue to work hard, they'll continue to improve these things, they'll continue to push towards those perfect quantum devices that indeed will make your emails unsafe. And towards that end, we are in the process of developing an undergraduate and graduate certificate program in quantum information science. The idea is to take people who are not physicists like me, but who are engineers and computer scientists, biologists, chemists, people with some background in technical fields, but a distinct background, and teach them the rules of quantum mechanics. We can very quickly teach them the way the world works on a quantum computer, what that noise looks like, and so on. And then they can use their expertise in these fields to make some really cool discoveries that we physicists are simply not trained to do. And I will say one of the big reasons that we're incentivized to do this is that the job market for quantum computing has exploded in the last few years. It used to be, it was just a few technical companies. Now, Google, IBM, even such companies as ExxonMobil, Toyota, have quantum computing divisions because they see that the future of some of these business logistical problems is to use the rules of quantum mechanics to solve these very complicated challenges. So our goal is to prepare students for all of the other expertises that we don't have, microwave engineering, programming, algorithm design, and teach them that little bit of quantum mechanics they need to understand how that would work on a quantum computer.